Lottie Mertens. She's from the University of Amsterdam, but also a connection with, where is it from?
IFW?
Dresden. So thank you. Speaking the quantum measurement problem. Right.
Great. Thank you. And thank you to the organizers for organizing this nice conference and for all of you to sticking out to the last session. I would like to tell you about some recent work we published on the quantum measurement problem. And of course I know that most of you are familiar with this troublesome transition, but to get everyone on the same page, I will shortly recap what it is. So of course we know that we have quantum particles, and we have this amazing quantum mechanics that is the best tested theory that we have. It works perfectly well. But then on the other side, we have classical objects, such as the chairs you are all sitting on. And they behave very differently, and we never observe them in a superposition of two different states. But in the end, these chairs are also made up of quantum particles. So why is this different? And especially, where does quantum start to become classical? And that is the quantum measurement problem, the inability of us to explain where this Heisenberg plot happens, but also how this transition happens, and if we do a measurement of the quantum system, why there is a single outcome and which outcome that is. Okay, so I'm one of those cat killers, I'm also vegetarian, I hope that makes it better. But yeah, our goal is to describe a model that explains this collapse. So I'm assuming that this collapse is a physical process, that it happens and that I can describe it. Then we want to dynamically explain how something goes from a superposition of states dynamically towards a single classical end state. And we do this by adding a perturbation to the Schrödinger equation called G, and then see how the dynamics change. Okay, so it's a very old problem, but now especially it's a very good time to work on it again. And that's maybe also why in the recent years I think it has picked up in interest again. And that is because we're actually getting experimentally close to this classical to quantum transition. So, before we could do only experiments for very small things that actually have something to do with quantum interference, and like this huge gap where we don't know what happens, but we're getting closer and closer to bridging this gap, and to hopefully therefore also finding some signature of this quantum collapse, or not. That's also interesting, of course. And we do this by studying a well-known physical principle, which is the principle of spontaneous symmetry breaking. Okay, so spontaneous symmetry breaking is well known in condensed matter, and we will use it to see if we can say something about the quantum measurement problem, because we have observed that the two are actually very similar. Okay, so spontaneous symmetry breaking explains that the Hamiltonian H is unstable under certain perturbations. So if you add a perturbation, you can show that the ground state of the system is not necessarily an eigenstate of the Hamiltonian. And that actually reminds us of collapse, because classical systems neither have to be. But this is all equilibrium. It has nothing to do with collapse, nothing to do with measurement yet. So what we now need to do, if we actually want to consider this, is to see if the Hamiltonian can also be unstable in time. Or another way of phrasing that, is the Schrödinger equation stable against small perturbation? Okay, so what we do is we have this nice equation, and we added this perturbation. And now to make it different from equilibrium spontaneous symmetry breaking, we have to make it non-unitary. So we make it anti-unitary by putting this I over there, which breaks the unitarity, and therefore, like playing a movie forward and playing a movie backward will be different time inversion as program. We need that if we want to explain measurements, because it's a many-to-one map. So this perturbation breaks unitarity. We can consider what happens if we then look at dynamics of this toy model. So it's a harmonic crystal, and with this initial superposed state. So here we just have position, and this is the absolute value of the wave function. We can see it's initially in a superposed state. And now we're going to turn on this Hamiltonian. We're going to see how does this time evolution behave if we numerically calculate that. And what you can see very nicely is that in this blue line here, it decreases almost to zero, while the other peak shoots up. So now we change.
Now preserving?
Yeah, here it is. Yeah. Yeah, what you can see is that you go from superposition to one end state. And you can see at what time scales this happen. So the localization time, as we call it, is proportional to 1 over mg, with n the number of particles in the system, and g is the strength of the perturbation. And of course we want normal quantum mechanics to still happen for small systems, like we don't want to change that at all, right? So we make this g very small, just like in spontaneous interbreaking, such that it's an infinitesimal perturbation onto normal quantum mechanics. And if this n, the number of particles, is also small, nothing will happen. However, in the thermodynamic limit, n becomes very large, and then this can have a significant effect, because then this localization time goes down, and we can see that it happens at finite timescales. If we move a little bit further in time, we can see that something else happens, something that we didn't really expect, which is that this peak can move. So the classical state is maybe a chair where you're sitting on, and this shows that the chair will move in space while you sit on it. And of course, that's not something we like. But we can also calculate on what timescales this will happen. And we see that it's not 1 over ng, but 1 over g. So as long as this g is infinitely small, it will happen on timescales that are not accessible to us, and the chair will not move. Okay, so far what I've told you is a fact. And I hope nobody will argue with me about it, because it's a mathematical fact. If we add a perturbation, then we can show that time evolution is unstable under non-unitary perturbation, and that such a perturbation causes collapse of macroscopic superpositions into a single localized state, and that then is stable to further perturbation because the time it takes to move away again is very large. Okay. So
which one collapses and which one grows?
Let's talk about it later.
What operator does this? You said you can find an operator G that does this?
Yeah, sorry, the G couples to the order parameter of the system. That's very important. Yeah, and therefore it reduces to the classical state.
I'm a chair, I should be a chair.
Okay, so if there's any non-unitary perturbation that couples to this order parameter, then macroscopic superposition will spontaneously collapse. Okay, from now on what I tell you is not a fact anymore, that's a hypothesis, because I'm gonna assume that this is there, that this is out there. And now I'm gonna try to connect this to the quantum measurement problem. So, can this instability actually explain dynamically what happens if we collapse a wave function? Okay, well, to see if we can do this, of course, we need to state what are the requirements we are actually trying to fulfill. And first of all, that is the preferred basis. So we want that the classical states that we see around us are the symmetry-broken states of the system. So the end state of collapse. And this happens immediately if you couple to the order parameter. Just like in normal spontaneous equilibrium symmetry breaking, these are then the symmetry-broken state. So that is true for the system. Now, if we look at stability, we want the chair not to move. We also saw, that's true, it only happens at very long time scales and we're not going to observe it. However, Born's rule, I haven't told anything about probabilities, as already noted. Only one thing collapsed so far, so we need to look at that from a different way. Okay, so for now I talked about our Monte Crystal, toy model, one thing, but now I'm going to generalize to any two-state system and consider the dynamics on that. And if we have two-state systems, it's very nice to represent this on the Bloch sphere. Also don't have to worry about normalization there if we include it in other ways. And here we have the Bloch sphere again. So up here at the zero we have the classical end states, the symmetry broken states. Of course this will become the delta function there. And here on the sphere we have all kinds of superpositions of the two classical states. So you can be on any point of the sphere, and the flow lines give you the evolution of those states. Okay, now this is just normal, unitary, linear, deterministic evolution. So you get these lines that turn around and turn around and turn around, and nothing really interesting happens there. Our toy model from before, we can add a non-unitary term. What you then see happening here is that you've created a sink and a source. So everything now flows wherever you are on the sphere to this sink here on the top. No matter where you start, no matter what you do, if you have this system of evolution, you will flow up. And that's nice, because now we have a preferred basis, which is the zero. It's a classical end state. And we have stability, as we saw. But of course, everything flows up. That's not even close to Born's rule. So to have that, we need to add something stochastic in the time evolution. Well, and a naive guess of doing this, which turned out to be not enough, is to change the direction of the flow lines. So far we could only collapse up, but now we can collapse up or down. And if we vary that every time step, so every time step we have flow lines that go up or go down, we can see if there's a probability of ending up either to the up or the down pole. We've done that by running numerical simulations where you cut off the evolution whenever you come close to one of the poles. And what you can see here is the result. So this is the initial value of these states, and this is the probability that you end up on top. And the black line is Born's rule, straight line. And the colorful lines are the result of our numerical simulation. What you see here is that the closer you cut it off to the pole, so the lower this number here, the more you deviate from Born's rule. And in the end, it actually becomes a flat distribution, so it's very far away from that. Also, you lose stability. Because of symmetry reasons, you always can either move up or down. So, yeah, not a good guess, right? However, this is only numerical simulation, and we can actually also prove that this is not possible. So we can prove that it's not enough to have linear dynamics, so dynamics, and give Born's rule. And therefore, we have to add a nonlinear component into this G. It's a requirement, we have to do it. And this nonlinear term, what it does is it introduces a separatrix on this log sphere. So what you see here is that now we have a third fixed point, which is unstable. And now this is a sink, this is a sink, and this is the source. So everything above the separatrix will flow up, and everything below the separatrix will flow down. And now we have this distinction, depending on where you start, you either go up or you go down. So that already has a lot more futures in it. And if we now change this line stochastically, we can actually get Born's rule, which is very nice. So it's possible to have Born's rule with this very simple model if you introduce non-unitarity, stochasticity, and non-linearity. You need all three. And what we've actually also shown is that the three are sufficient. Okay, so far this was only very mathematical, like I just gave a model, but let's make it more precise. So here is a toy model of a lead Mattis antiferromagnet, where we include, this is the G generator that we have. So there is no I here because the I is gone on the left. And here, this is the non-linear term with the expectation value of the spin on the A and B lattice. And this here, B, is the stochastic field. So it changes variable. And this is the order parameter, so it gives you the classical end states. You can simplify this to this nice form where you see all the futures better. And this works. It gives you stability, the right end states, and Born's rule for certain B. And that's nice, but of course there are already other objective collapse models out there. So let me highlight what is different between ours and the others, such as DRDAR, GRW, and CSL. Which is that these non-linear term and the stochastic term here, they are uncoupled. So they do not multiply each other. They are separate terms into the equation. And therefore the stochastic term does not depend on the states it works on. So if we have a magnet and it has an initial distribution or another distribution, the field stays exactly the same, which makes it a lot easier to actually explain such a field, because it can be some global field that is everywhere the same. So that's a nice feature. that the stochastic term does not depend on the state. So let me summarize that. I first told you observation, which is effect, which is that Schrodinger's equation is unstable. And later I told you the possibility of using this instability to explain that the spontaneously unitary violation might explain quantum measurement if they have a specific form such that they are non-unitary, non-linear and stochastic. Okay, in future we're going to generalize this, so we go from 2-state to n-state. And the last talk today by my colleague Avito will be about this and also a master equation form of this. Thank you.
I think we have time for one question. Here we go.
Can I just speak and save time?
No.
I was under the impression, maybe I'm wrong, so please correct me. If you modify the Schrodinger evolution to be generalized to non-unitary, stochastic, non-linear, assume norm preservation and no superluminal signaling, you should have got CSL. So maybe I'm wrong. So you have norm preservation and no signaling.
Well, this form doesn't have a norm preservation, but we can write one down, which is not CSO.
It's not clear. Maybe my ignorance. Why?
I think the next talk by Avito will go more into this, so I hope then your question is more explained and else we can talk after.
Yeah, thank you.
And discuss exactly this.
Okay, very good.
Okay. Well, thank you. I think we are at our time limit, so let's thank the speaker again.